Okay, welcome back. So today we're going to start talking about the fundamental theorem for line integrals. So before we jump into the actual theorem, so let's just give ourselves a title here. This is the fundamental theorem of line integrals. So before we kind of jump into the actual theorem, the first thing we're going to discuss is path independence. So yesterday we started talking about these line integrals, these integrals that add up along a very specific curve. So now what we're going to do is consider two points A and B in a region that we'll call D, and the work done by moving from the point A to the point B. Within a field F. So let's kind of sketch out what's happening here. We have X and Y, and then we have some region D here. And within it is a point A and B, and we're trying to find the work done from A to B along what we'll call the path C. So from yesterday, we learned that the work done by this force vector, this vector field, is the line integral over C of F dot dr. So there's one question we could ask ourselves. Is there some property F can have that lets us take any path for the same amount of work? Right? The vector field F, basically we're asking what kind of property would we need to say the work done from A to B is the same regardless of the path that we're going to be taking. So to dive in, let's first if this is true, any two paths give us the same work. Which is to say that if I have some line integral over some path C1 of f dot dr, this is the same as the line integral of some different path C2 of f dot dr. Now remember, it still has the same initial and terminal points. It's just that we take a different path from A to B. So a sketch of what's going on here is maybe we're going from A to B. Maybe this is C1, something like that. And then my other path maybe comes over this way and does C2. So C1 and C2. But the cool part about this is if I go in the reverse direction of one of these, I end up with a closed loop, meaning that I end up back at the starting location A. So these paths can be viewed as one closed curve. So for instance, we could take the integral of C1 f dot dr, add negative C2, this line integral in negative C2, so we're going in the opposite direction, f dot dr. This could be formulated as a new line. So maybe if we go all the way around, something like that, we'll call that concept the curve C. This will be C. And when we have a closed line integral, I don't think your book uses this notation, but this is very common. You put a circle here. This just means a closed line integral. That means the path that's taken makes a full loop. F dot dr. Now, if this first integral, remember we're saying that these are giving us the same work. So if this first integral gives us a w for work, and then the second one is the negative path, that should certainly give us negative w. So that means that this total should be 0. If f has this magic property. Later on in this chapter, we'll get a definite answer of how this is brought about. But for now, the only way that f satisfies this is if it's conservative. So the only way our closed line integral of f dot dr is equal to 0 for any closed curve, not just a generic, like the one that we've picked, but for any closed curve is equal to 0 is when f is conservative. So we brought up conservative vector fields yesterday, and we learned that it was able to be decomposed. So kind of recall that if we have that f is conservative, we know that f can be expressed as the gradient of some scalar function, lowercase f. Okay, so now with this, we have that some open line integral f dot dr is path independent when f is conservative. Which means to say, if we wanted to look at this line integral here, and it's over some crazy curve C that we don't want to deal with, if f is conservative, what we could do is just pick a new curve that goes from A to B, same initial and terminal points, and do the line integral on that, rather than the more complicated curve. But being a conservative vector field is a very special property. As you can imagine, that this kind of falls out. For conservative, does that mean it's equal to its gradient or that it has a gradient? Neither. Conservative means that you can write it as a gradient of a scalar function. So you can't take a gradient of a vector field. Gradients only act on scalars. So it doesn't, not necessarily that this capital F has a gradient, because that you can't have that. You can't have a gradient of a vector field. It just means that there is some lowercase f, some scalar function that exists so that I can write my vector field in this way, right? It's not given to us that, so it's not given to us that this lowercase f. So we might have this capital F, but we don't have this lowercase f. So this is one definition of conservative, and we're going to see some other ones as we go through the course. But for now, it means that it can be decomposed as the gradient of a scalar function, lowercase f. Okay. So why is this so important? So this brings us actually to our theorem. So before we kind of discuss what the theorem is and what it kind of does, let's figure some stuff out. So recall the fundamental theorem of calculus. So if we had just an ordinary integral from a to b, and I had some scalar function, capital F, and its derivative, dx, the fundamental theorem of calculus said that this was the antiderivative of the first derivative of f, which ends up just being f, at b minus the function at a. So it basically just meant that derivatives and integrals pretty much cancel out, right? So why is that important here? Well, if our vector field capital F is conservative, then it could be written as the gradient of some scalar function f. So notice then if I have my line integral over C, so f dot dr, I could instead write this as the line integral over the same curve C, but now I replace capital F with the gradient of my scalar f dot dr. So remember, the gradient is still this vector, right? So I'm taking the gradient of this f function, and then I'm dotting it with this dr. So if this is true, then we already know that it's conservative, meaning that the path that I've taken doesn't really matter. I have path independence. Well, what we could do is kind of view this gradient as a derivative, kind of in the sense of this fundamental theorem of calculus. So what we're going to do is write out the gradient of f dot dr. What is this? Well, this is the gradient of f dotted with r prime of t dt. So if we went ahead and parameterized our curve, we can go ahead and write the dot product with dr as the dot product with r prime dt. So now let's actually do this dot product out, recalling that the gradient of f is a vector from the first derivatives of each of the component functions. So here we have fx times x prime plus fy times y prime plus fz times z prime. And we're going to stop there, but this argument still holds for higher dimensions. So you can keep going here. Right, because r prime just has x prime, y prime, z prime in it, and this just has fx, fy, and fz. So we dot that out, we get this sum here. So the way that we're going to write this is basically we're not doing anything here. We're just kind of rewriting what each of these mean. This is partial f, partial x, dx, dt, plus partial f, partial f, partial y, dy dt, plus partial f, partial z, dz dt, dt. Just rewrote it, but look at the thing that's in the square bracket. Does that ring any bells? Does that look familiar to us at all? It should, right? This is the chain rule. It's back. So we could actually write this as the t derivative of f of x, y, and z, still this dt at the end, and I left these blanks because we're doing, these are all functions of t, right? So if you think about it in reverse, if you went ahead and you needed to know the time derivative of this quantity, you would have to use the chain rule here. So let's go ahead and insert this back into our line integral. So if I said the line integral of the gradient of f dot dr, if I did my parameterization, this goes from some a to b in time, and then I have d dt of f. And notice that this is x, y, and z, or otherwise I can kind of write this as the parameterization inside of f. A little shorthand. dt. Right, well, I'm taking a time derivative and then I'm taking a time integral, or at least just a parameterization of this t. This just means that we can use the fundamental theorem of calculus, the normal fundamental theorem of calculus, to get us to that this is f with r at time b minus f with r at time a. So if capital F is a conservative vector field, it can be decomposed into the gradient of this scalar f, and then we can use the normal fundamental theorem of calculus to get us to this point. So if our vector field is conservative, such that we have that the vector field can be decomposed into the gradient of f our line integral just relies on the start and end location, which makes a lot of sense, right? We said that if f is conservative, this has path independence. So it doesn't matter what path we take. So the only contributing factors there should be the initial and terminal point. And we see that in the fundamental theorem for line integrals. So if f is conservative, we can write it as a decomposition, as a gradient as a scalar function. And then we can use the normal fundamental theorem of calculus to get us to this point. So this is our theorem right here. Okay, so when is f conservative, right? Are there any tells for us to kind of rule out if f is conservative or not? So if we're in R2, and we're going to learn a lot more about conservative vector fields once we introduce some more concepts, but for now, we're only going to kind of rely ourselves in R2. So if the vector field can be written as P and Q, functions of X and Y, so these are the component functions. If partial P, partial Y is equal to partial Q, partial X, then F is conservative. So this is just one way for us to kind of check here. So let's do a quick example. If I have that capital F is 3 plus 2x times y, and x squared minus 3y squared. So remember, this is P and Q, or this should be minus right there. Then Py, so I'm taking the y derivative here. This just gives me 2x, and then Qx. So I go ahead and take a x derivative here is, so I still get a 2x. So these are equal, so this means that this vector field here is a conservative vector field. Okay. So with that, let's do an example where we use the fundamental theorem for line integrals. So we're going to find the line integral over C f dot dr where f is the conservative vector field that's given by 2x e to the xy plus x squared y e to the xy, comma, x cubed e to the xy plus 2y. And C goes from 0, 0 to 1, 1. So C could be the most complicated path, right? And we don't really want to take it along that path. Now, if it's conservative, it is path independent. So you could take a straight line from 0, 0 to 1, 1, and then try to brute force this line integral by doing a parameterization. But parameterizing this might be a little tough. So instead, what we might want to do is, because it's a conservative vector field, we can use the fundamental theorem for line integrals. Remember, that means that we can decompose capital F in terms of a gradient of a scalar function and then take it from there. So this problem kind of reduces to what is the scalar function lowercase f, where this is its gradient. So let's go ahead and see if we can figure that out. So since our vector field is conservative, there is a scalar function such that its gradient is equal to our vector field. Okay. So I'm going to go ahead and just write these two things out on top of one another. So we have capital F. So I'm going to rewrite this here because I think it's important to see the relation here. So this again is our vector field that we're considering. The gradient of the function that we're looking for is partial x of f and then partial y of that function, right? And we know that these are equal, which means their component functions are equal. So right off the bat, I know that the first derivative with respect to x is this thing here. I also know that the y derivative is this thing here. So what we're going to do is we're going to pick one of these. I always typically pick the first one because it's the first one, but you could always do this reversed or in any order. The first thing I note is that f sub x is equal to 2x e to the x times y plus x squared times y e to the x times y. Okay. So if I wanted to figure out what f was, I would have to take an integral of this. So I go ahead. So scalar function f is equal to the integral with respect to x. of the first derivative with respect to x. So I go ahead and substitute that in. This is 2x e to the x times y plus x squared times y e to the x times y dx. So to do this integral out, what we can do is note that if I wanted to find the partial x derivative of x squared e to the x times y, this is equal to 2x e to the x times y plus x squared times y e to the x times y. And that's what we have right here in our integrand. So I know that f is equal to x squared e to the x times y. But we're not done yet. This was an indefinite integral, remember? So in Calc 1 and Calc 2, you always had that plus c, right? So we're doing an integral with respect to x, right? So anything that's a constant can be added to this, and it would be very similar with respect to x. So that means a function of y could possibly be here, right? And you can verify that. If you go ahead and take an x derivative of this, this goes away, just like it was a constant, right? Because with respect to x, it is a constant. And then we would take the x derivative of this, and we'd go ahead and get our fx right here. So because we took, just to kind of reiterate, just because we took a derivative with respect to x, we add a constant with respect to x, which is any function g of y. It could just be a constant with respect to both x and y, but we don't know. So we have to keep it general here. So this is some g of y function. So how do we find this g of y now? Well, what we could do is that this is our new candidate for what f is, right? We can use the other piece of information that we have, which is to say that fy is equal to this thing here, the second component in our capital F function. So we go ahead and we'll take our function here and we'll take the y derivative of it now. This ends up giving us an x cubed e to the x times y plus g prime of y. But like we said before, this needs to be equal to the second component of our capital F, which was x cubed e to the x times y plus 2y. Well, these two terms here, this exponential terms, and look like they end up canceling, and all that's left is that g prime of y is equal to 2 times y. Well, if g prime is 2y, then g of y is equal to y squared plus some constant. Perfect. So now this gives us what g of y is. We can go ahead and plug that back into our candidate. So this meant that f of x and y is therefore x squared e to the x times y plus y squared plus c. So now we can use the fundamental theorem of calculus, or for line integrals for this. So now we've got that our line integral over c of f dot dr is equal to f at the point 1, 1. So this is our terminal point, minus f at 0, 0, which was our initial point. So we can go ahead and plug those in. This is e plus 1 plus c minus just c, which gives us e plus 1. So without actually doing a line integral, we've done the line integral. Right? We didn't have to brute force this. We just used the fundamental theorem for line integrals to get our way through this problem. Okay. So I see that Heather is on now. The next segment takes probably a little bit longer than 5 minutes. Can you explain what happened when you used the partial y derivative? Oh, okay. I've got a lot of questions coming in now. All right, let me answer these, and then we can go on our break. So how did you get that fy is equal to this guy here? So this is the question. How did I get this? I just took a y derivative from this line. Right? I know that this is my candidate for f. I don't know what the g function is. So in order to find what this g function is, I'm using the only other relevant piece of information that I have, which is this here. I know that these things are equal to one another. So what I do is I take my candidate for the scalar function f, I take its y derivative. So this gives me this right here. Okay. But I also know that fy is equal to this thing right here. So I can set it equal to that. This means that I can just algebraically solve for g prime, which is just equal to 2y. And then because I know this is a function of just one variable, it's just reliant on y, I can take its y derivative, but I have to add a constant. So that's why I get this y squared plus c. Can you explain what happened when you used the partial y derivative? I think those questions were related, unless I'm mistaken. Right, so this is, all I did was, I need to find what this this lowercase f is. Okay, so I used the first piece of information, which is that their x components are equal. So I know that fx is equal to the first component of my vector function. So then I have this here, but I want just f, not f sub x. So I take a an x integral. But I need to make sure that I add a plus c, where c is a constant with respect to x, which limits us to any function of y. So then this is my candidate. This is my updated candidate. So I have to find what g of y is, and I use my other piece of relevant information, this guy here, to do so. Right? Take a y derivative of our candidate and set it equal to what the known y derivative is. And that gives us a way to solve for g. Ooh. Hillary, I think if I'm not mistaken, I think we're going to be talking about that concept later, because we haven't introduced the tools necessary. But that's a good question. Yeah. So that means, right, yeah. It's very reminiscent of fluid mechanics, because we're going to be talking about what's called like curl and divergence, and those are going to play a role in all of this, specifically curl. Right, so we're going to see that later. But yeah, that was a good question. Okay, so then with that, why don't we take our 5-minute break, and then Heather and Teddy can start our recitation.